In this video, we're now going to talk about bicyclic compounds. And there are three main classes of bicyclic compounds, although you could say there's really only two of them, and I'll talk about why that is in just a little minute. The first one is a Spiro compound, and that's one in which you have two rings that share one carbon. Then you can have a fused bicyclic compound where two carbons are shared between two rings. And you can have a bridged bicyclic compound where there's going to be more than two carbons that are shared. Now, oftentimes fused bicyclic compounds are a subcategory of bridged, where essentially you have uh, zero bridges, which makes it a fused compound. So oftentimes you'll see in places people just saying that there are Spiro compounds and there are bridged compounds, and a fused bicyclic compound is part of the bridged compounds. So let's take a look at Spiro compounds first. And of course, if we think about the simplest way of drawing two rings with one carbon sharing, we can start with this type of structure where you have two cyclopropane rings and they are being shared by that one carbon there, right? And then, of course, we could go further and we could have a cyclobutane and cyclopropane ring sharing one carbon. We can have cyclohexane and cyclobutane sharing one carbon, and so on and so forth. These are Spiro compounds. And it happens that Spiro compounds actually are not all that prevalent in nature, although that is certainly something that is an ongoing investigation. More and more natural products are coming out that have Spiro geometry, and I'll show you a couple of those in just a little bit. But when you think about the geometry of these Spiro compounds, you see that the two-dimensional image is actually a little bit misleading. So understand that that the geometry of that carbon is still tetrahedral. So when we draw a tetrahedral carbon, we have two carbons that are in the plane, but one carbon coming out of the plane and one going back behind the plane. And therefore, if we were to simply look at that first structure with the two cyclopropane rings, we would have to draw it like this, where we see that the two rings are in different planes of one another. One's in the plane of the board and one is perpendicular pretty much to the plane of the board. And of course, this lends itself to a lot of stereochemical features. And one of the things that chemists really love is to say, okay, well, what if I have a situation where I could make a Spiro compound? Can I control stereochemistry that way? And so here I'm going to simply show you a couple of natural compounds that are Spiro compounds. This particular structure right here, notice I have a cyclohexene ring, and bound to that is a cyclopropane ring that's sharing a bridgehead. It's called a bridgehead. Any carbon that's shared is called a bridgehead. And there's stereochemical features that are built into to the basic backbone of the Spiro compound. This particular structure is called agarrospiral. Agarrospiral, and we call this a spiroterpenoid. Terpenoids are a class of compounds that we'll get into later on. But this is isolated from agar wood, which is where it gets its name, and it for many years has been used in Chinese medicine and Asian medicine as a sedative. The next structure also hails from Asian medicine. This is called bacchanalide A, and there are obviously different stereoisomers of bacchanalide. This is one particular naturally occurring stereoisomer, and it happens to be isolated from the Japanese bog rhubarb, which they call fuki. I just thought that was kind of interesting. But you see that the kind of cool geometry that takes place with these Spiro compounds, the built-in stereochemistry of them, and you can definitely see the complexity that nature provides with all these types of natural products and the various stereochemical components to it, which is pretty cool to understand that. So those are Spiro compounds. And of course, the next category would be fused bicyclic rings. Um, and the simplest fused bicyclic ring would be when I have two cyclopropanes that are, again, joined by two carbons. And I could have a cyclopropane and a cyclobutane ring joined by two carbons. And I could have two cyclobutane rings joined by two carbons, and I could go on, having two cyclopropane rings. And we see that, the bridge heads, now there's, instead of one bridge head, there are two bridge heads. We call them bridge heads. And hopefully you can recognize the two bridge heads in the other fused rings, bridge heads here and here, right? Now, interestingly enough, if we think about stereochemistry, the hydrogens at the bridgehead can either be cis or trans to one another. We don't see that in smaller rings, but we do see that when we get into six-membered rings and on up. So the simplest fused six-membered ring system looks like this. It's called decalin. Why is it called decalin? Because it has 10 carbons. 10 total carbons on it. But it's essentially two cyclohexane rings that are fused together. So we can have cis decalin, right? So where the two hydrogens are on the same side of the plane, either a wedge or a dash. Of course, we have some stereochemistry going on there. So this is cis, and then we have trans, where the two hydrogens are on opposite planes of one another. And that's typically how they're drawn in kind of a bond line formula. But, of course, we know that these cyclohexane rings are not planar. So one question is, how do you draw the chair conformations of decalin? Well, I start with a normal chain. And I say, okay, if I'm looking at trans decalin, then I can have a methyl group be equatorial down and a methylene group be equatorial up. So notice the hydrogens are in the diaxial position. One is above the plane, one is below the plane. And then I simply draw a fused chair conformation right next to the one that I just drew. So this is trans decalin. This is the only conformation that trans decalin could take, because if you think about doing a ring flip on this, that would mean that the methylene groups would be diaxial. And in order for the ring to be diaxial, it's actually impossible to do. So diaxial conformation is impossible. This only exists in the diequatorial conformation. Now, when I think about cis decalin, things get a little bit more interesting. So here I'm drawing the hydrogens cis to one another, right? One hydrogen is axial, the other hydrogen equatorial. When I think about the ring and where the ring is, I see that, well, there's going to be a methylene group that's axial and a methylene group that's equatorial. And now I somehow have to connect them to form a ring. Well, I can make a chair ring simply by drawing a line parallel to the adjacent carbon. And then I'm going to draw one parallel to my axial carbon, and then I'm simply going to join them together, right? And so you see it takes a little bit of getting used to, but that's basically how you would draw cis decalin. And there's all sorts of chemistry associated with cis-decalin, and there's a lot of chemists that are kind of exploring the difference between the two, just in terms of geometric shapes, which is kind of a cool thing. So cis-decalin, right? And that's those are examples of fused rings. Now we get into bridged rings, and a bridged ring has shares 3 carbons. So we can think of 2 cyclopentane rings that can share 3 carbons. Basically, the smallest ring you can have that shares 3 carbons is a cyclopentane ring, and it happens that what you get is something like this. So if I take a look at the envelope conformation of cyclopentane, and I think about 2 envelopes coming together, then I can draw another envelope that looks like this, right, from the back side. These are 2 cyclopentane rings, and they are sharing 3 carbons. Now, it happens that there are 2 bridge heads, and then we have a bridge. So the bridge is typically going from the smallest number of carbons going from one bridge head to the next bridge head. And so you see that there's 1 carbon that's separating each of the 2 bridge heads. And we can think about the geometry of it. There are 2 hydrogens coming out, so 1 hydrogen's coming out at me, and then the carbon that's further away has a hydrogen that's going even further away. These types of structures are very common in natural products, and so you see them all the time. And as a matter of fact, we've drawn this structure before thinking about alkenes and alkene stability, and we saw that you can't put a double bond at that bridgehead based on the incorrect overlap of the p orbital on the carbon on the left with really an sp3 hybridized orbital on the carbon on the right. Now I can have bridge compounds that have different sizes of bridges. So here I see these are the bridge heads, and now I have a compound that has a 2 carbon bridge, because that would be the smallest one. And of course I can have various ring sizes. So here I have the bridge heads right here, and there's a 1 carbon bridge there. So one of the questions is, well, how do you name compounds like this? Could be kind of daunting to figure out how to name them. And naming bicyclic compounds isn't that hard if you understand some of the rules that you simply need to apply. So the first thing that we do is we count the total number of carbons in that ring system. And this is what gives us the base name, right? So we're counting all of the carbons in the ring, regardless of where they're located in the ring itself. Not substituents coming off the ring, but carbons in the ring itself. And so that's our base name. And then what we do is we number from a bridgehead carbon, which would be, we label carbon number 1, and we go along the longest bridge first, and then the next longest bridge, and then the shortest bridge. So we end on the shortest bridge. Then we assign each bridge a number equal to the number of carbons. And of course this, the tricky part here is we have to exclude the bridge heads. We don't include the bridge heads when assigning a number, and I'll show you examples of this in just a little bit. And so what you do is, once you have those numbers, you put them in brackets in ascending order, separated by periods between the bicyclo prefix and the base name. Oh boy, all right. How does this all work? Well, let's take a look at an example. Here I have a bridged bicyclo compound, right? And I see that really it's a cyclopentane ring and a cyclohexane ring kind of fused together. Well, how would I name this? I start out figuring out what my base name is. So I count all the carbons that are in that bridge compound, excluding the substituents. And so I see I have 8 carbons. So the base is going to be octane. Well, now what do? Well, now I have to count the number of carbons in all of the bridges. So there are 3 bridges here. And I'm going to draw this structure out again, highlighting my bridge heads. And so what I do is I count the longest bridge first. So I have on the right, I have 3 carbons, and then I get back to one of the bridge heads. So from a bridge head, 3 carbons to a bridge head. So that we call a 3-atom bridge. Notice I'm not counting the bridge heads. I'm simply counting the carbons in that bridge, excluding the bridge heads. So on the on the left-hand side, I have 2 carbons. So this is a 2-atom bridge, or 2-carbon bridge. And then the last bridge is only a 1-carbon bridge. Okay, so now I can start putting these things together. I see that there are 2 methyl substituents. Both of those methyl substituents are on carbon number 3 because I have my numbering system. Notice I start at a bridgehead and I go from the bridgehead to the longest bridge, back to a bridgehead, to the second longest bridge, and then I count that 3rd bridge. All right, so I have 3,3-dimethyl bicyclo. Right, so I put the substituents first, then bicyclo, and now I have to list the bridges. I have a 3-atom, a 2-atom, and a 1-atom. So the way I list it is in brackets 3 period 2 period 1 from ascending order to descending order, and then my base name is octane. And that's how you name a bridged bicyclic compound. 3,3-dimethyl bicyclo, in brackets 3 period 2 period 1 octane. Let's look at another example. Here I have another bicyclic compound, so I'm going to figure out how to number, and notice I could there are 2 bridges that are 2 carbons long, but one of them has a substituent on it, and therefore I'm going to start numbering at the bridge head, and then I'm going to go to the carbon on the right as C2. So then I go along, C3, C4 gets me back to a bridge head. Then I have to go to the second longest bridge. So I go 5, 6, then I go to the shortest 7. And that's why that 1-carbon bridge is labeled C7. So that's where I get my numbering system. And so I see that there's 2 methyl groups. One methyl group is on the 2-carbon, one methyl group is on the 7-carbon. And therefore I get, and so I look at how many bridges I have. I have a 2-carbon bridge there, I have a 2-carbon bridge there, and I have a 1-carbon bridge there. So it's going to be 2 period 2 period 1. Putting it all together, I have 2,7-dimethyl bicyclo, 2 period 2 period 1. Then there are 7 carbons, so my base name is heptane, and that's how I name that cyclic compound. Now, I can also name fused compounds in a similar manner. And here's an example of a fused compound. Of course, there's stereochemistry involved. There happens to be stereochemistry in that second structure as well, but we won't get into that quite yet. So here I have stereochemistry, and of course I can find the absolute configurations. But first I want to take a look at, here are my bridge heads. So I can number this. How do I number it? I have to start at the longest bridge and then go to the second largest. And now my third largest, there are no carbons. So I'm going to start numbering 1, 2, 3 all the way around. Notice I have a 4-carbon bridge. I have a 3-carbon bridge. And then that third bridge has no carbons on it. So I number 1, 2, 3, 4, 5, 6, 7, 8, 9 all the way around. 9 carbons. My base name is going to be nonane. And then I can assign absolute configuration. So the carbon on the left has an absolute configuration of S, right? Because bromine is going to take number 1. The carbon number 2 is going to be priority number 2, and then carbon number 4 would be priority number 3. So I'm rotating in a counterclockwise fashion, so that's S. And then, of course, C9 is going to be R, right? So I have C3 having an S absolute configuration, C9 having an R absolute configuration. And so I say 3S, 9R, 3 bromo, 9 chloro, bicyclo. Now I have to give the brackets, the number brackets. And so it's going to be 4 period 3 period 0. So there's always 3 numbers in a bicyclo compound, notice. Even in fused. So with fused, the last number is going to be 0. That signifies that you have a fused compound. And then, of course, my base name is nonane. That's how you name bicyclic compounds.